So we were talking about extensive form games, that is, games in which agents had information about the actions of some of the other agents, well, some partial information or full information of the agents that took an action before them. Okay, so the model we'll construct will contain more information. It will be more extensive, hence the name extensive form game. So last lecture, without giving the formal definition, we looked at two games and represented these with pictures. And that's actually what we will do for most of the time. Okay? So let me remind you the games. Sorry. So one was the entry deterrence game. I'm not going to go over it. Last lecture we talked about it. But we had a picture which represented this game, which modeled this game. So the game started with an entrant making a decision whether to enter or stay out of the market. So the firm could enter or stay out. So let me call this firm 1 or firm 2, it doesn't matter. So rather than calling it the entrant and the other firm incumbent, I'm going to use E for enter, and hence I'll call the firm that is deciding on whether to enter or stay out the market, firm 1, and the incumbent firm, firm 2. So if the firm 1 enters the market, then firm 2, the incumbent firm, it was its turn to take a decision. It could get into a price war with the entrant, firm 1, or accommodate, okay, operate under duopoly conditions, and then the game would end. If the firm stayed out, firm 1 would continue to be a monopoly, and the game again would end. There's no more decisions to be made. That's why the game ends. The other game we had was, again, a very simple, trivial game, voting game. There was a committee of 3 individuals. One of them was the chairperson. We called him or her Agent 1. So Agent 1 took an action, decided on for whom to vote for. He or she could vote for A or B. Both Agent 2 and 3 observed this and then decided on who to vote. So wrote their candidate on a piece of paper without showing to the other, and simultaneously their votes were simultaneously revealed. So when Agent 2 was casting a vote, he or she only knew the vote of Agent 1 but did not know the vote of Agent 2, and the same for Agent 3. The way we represented this picture was, we said, well, let's assume that we take the paper, the vote of Agent 2 first. He or she could vote for A or B, A or B in either case. And then we took the vote of Agent 3, the paper on which Agent 3 casted a vote. So it was Agent 3's turn to make an action. So he or she could vote for A or B. In any case, Agent 3 could vote for A and B. And the fact that Agent 3 did not know the vote of Agent 2, but did know the vote of Agent 3, we illustrated that with dotted lines, okay? So this is a picture representation of 2 different games. Now, we will do this in a little bit more formal way. Okay, so I'll give you the formal definition, but fortunately or unfortunately, it depends on what your tastes are, we will not have to worry that much about this mathematical structure. The pictures, as long as they're done correctly, will be sufficient for us. So an extensive form game is a long list of items, okay? Unlike a strategic form game, it's not a 3-tuple or 4-tuple if we're interested with outcomes. But most of the time, strategic form games consist of 3-tuple, and they were simple objects. Who's involved? What can each of them do? What is their preference over strategy profiles? Here, it's a longer list, and the objects are a bit more complicated, okay? So what is this? Well, the first element, just like in the strategic form game, denotes the set of agents. So it's a non-empty. We always assume that the set of agents is finite. It's a non-empty, finite set, okay? So there's no difference in the first item. The second item, okay, it's a more complicated animal. It's a set of sequences which represent, by the way, I will send this to you so you don't have to write them. It's going to be a long list. So H is a set of sequences which represents the histories, what has happened in the game, okay? And this sequence, to be a meaningful list of histories, has to satisfy certain conditions, okay? First, when the game starts, nothing has happened, okay? That we denote with the empty sequence, okay? So the beginning of the game, nothing has happened so far. So H should contain the empty history. So what I'll do is, as we look at the mathematical structure, we'll construct the example, okay? So the other thing is, well, let's look at the picture first and then go back here. So player one takes an action, okay? And hence something has happened, okay? What has happened? Player one has taken the action E, okay? So that will be denoted with the sequence E, okay? Or player one can take the action O, stay out. That's another history, okay? So history represents a state of the game, okay? So here we're at the state where the game has started and player one took the action O. Here we're at a state where player one has taken an action and taken the action E, and that's what the history is, okay? And then after player one taking the action E, player two can take the action F, which will denote with the history E, F, okay? So that's, when we follow this path, that's what has happened. The game has started, player one has taken the action E, and then player two has taken the action F, or EA. That's another history, okay? And actually, that's the set of all possible histories of this game, okay? So here, again, empties, that denotes this state. Nothing has happened. A, B, I should write sequence. Okay. AA, that's an history. AB, okay, that's another history. BA, BA, BB, okay, and then A, that's another history. Player one started, played A, then the next agent played A, then the next agent played A. A, B. First agent played A, then the action A was taken again, then the action B was taken again, okay? And then it keeps going on like that, so B, B, B. So that's a longer list, okay? So what properties does the structure satisfy? First of all, for example, if this is a history, any initial segment of that should also be history. Since we have we have observed this set of actions, this history, we should have observed its past. So EA is a history, then E should also be a history, okay? Okay, so AA is a history, the initial segment of this, AA, that should also be history, okay? We can't come to this state, we cannot have lived through this history without having lived through this history. We could not have arrived to this state without having gone through this state, okay? And again, for the same reason, this should also be a history, okay? So if such a sequence is in H, okay, if such a sequence is in H, then any initial segment of that sequence should also be in H. That's what this condition says, okay? Well, this is a little modified version of this. Here, this is a set of natural numbers. So what kind of a history, what kind of a sequence is this? This is an infinite sequence, okay? So most of the games that we will deal with will consist of finite sequences, but we might deal with some games of this one. So this is the same thing. If an infinite sequence is a history, then any initial segment of that is also an history. So these two say the same thing actually for finite, for infinite sequences. Oh, wait a minute, did I say that correctly? Yeah. Okay. And that's another version of saying it, okay? The infinite sequence is constructed by finite sequences of any length. Okay? So far, so good about histories? Okay, so the next, so just the terminal. So there are some special histories. That was the initial history. Yes, sir? Sorry, do we use?
This notation, do we use superscript as indexing?
Well, in general, we will have, for specific games, we will have this form, okay? But,
For example, let me write the sequence. In the sequence notation, the sequence element is
A super K, yes, that's what I did. One reason why I did it, usually when we had, for example, subscript, it denoted something about the agent, okay? So because this is not about the agent, it's an action, I used superscript. We could have used subscript too, but in general, I prefer to use subscript when I'm mentioning agents and superscript when I'm mentioning other kind of objects, okay? So far, so good? Okay, so it's still the sequence, but rather than in mathematics, you're usually used to subscript. I think that was the problem. Well, subscript, superscript, the essential thing is when you have a sequence, it's a function from natural numbers to some set of objects, okay? So you can write AK, A super K. You just should think that it's a function from the natural numbers to some set of objects, okay? So there is 3 different types of histories. One is the empty history, which denotes the beginning of the game. There could be only one such history. And then there is a set of histories called terminal histories, okay? Terminal histories are histories which are either infinite, okay? We'll see an example for that. Or is not the initial segment of any history. So this history is not a terminal history because it's the initial segment of this history. This history is a terminal history because there is no history for which this is an initial history. So this is a terminal history. EF is a terminal history because it is not the initial segment of any other history. That's terminal. And so is this because it is not the initial segment of any other history. Okay? Okay? Similarly, this history, A, is not a terminal history because it's the initial segment of this history and this one and this one and this one, but one is enough for us. Okay? Because of this, this is not initial history. So is this. This is not initial history because it's the initial segment of at least one history. Actually many, but I only care about one. Okay? This history is a terminal history because it's not the initial segment of any other history. So is this. So is this. Okay? So we have the initial empty history, the terminal histories. The initial history is only one history. There is the set of terminal histories which consist of many histories. And there are the other histories which we call action histories. So far, so good? Okay. So, the set of actions available. So when we see this history, E, this is an action or a history. It's not a terminal history. So because it's not a terminal history, it's the initial segment of some history. Okay? Actually, it's the initial segment of these two histories. So looking at this, we can conclude that without looking at the picture, looking at the structure, we see that at this history, whoever was taking an action had two actions available to him or her, F or O. I'm sorry, that's not O, that's an A. F or A. Okay? Okay? This is his initial segment of, well, the empty history is actually the initial segment of any history. But the histories which immediately follow that, which is of length 1 longer than this one, are those two. So whoever is taking this action, whoever was taking an action at this history, only two actions were available, E and O. Okay? So looking at the structure, for example, here, okay, start with here, okay, this history is an initial segment of, well, many histories, but the histories which are one item longer than this history are those two histories. So looking at this, I see that whoever was taking an action here, the actions available to him was A and B. Okay? So looking at the set of histories, we can deduce what actions were available to the agents which are taking an action at a non-terminal history. Okay? Looking at this structure, I find all the histories which are one item longer than this, which are BBA and BB, well, I already have it there, BBB. Okay. So what I conclude there from here is, at this history, I look at it, or I look at all the histories which are one unit longer than this history H. Those are those two histories. So I look at what is the difference, what is added, A or B is added. So I conclude that from the structure, at this history, the actions A and B were available, which we could observe from the picture. Okay, but if you didn't have the picture, if you had the mathematical structure, that's how you conclude which actions are available. Okay? So far, so good? So I said, okay, at this history, whoever is going to take an action, the actions available to him or her is A and B. But who is going to take an action? Well, in the picture, we took care of that by putting a label on each node which represented a history. So in the mathematical structure, we need a function which we'll denote with calligraphic P, okay, which is a function that assigns to every non-terminal history, okay, a member of the set of players union a player called chance. Okay? So in some games, agents play and then a coin is flipped or something random happens. Okay? Nature intervenes. Okay? So sometimes this would be enough. For example, in this game, chance is not involved. So our function P is a function from the set of all non-terminal nodes to just the set of players. Okay? But in some games, we will study some games where chance is also involved. So that's what we have. Okay? So that's a non-terminal history. So script P of the empty history should be assigned to a player. It's assigned to player 1. Script P of E, that's a non-terminal history. So we should assign a player to that. Player 2 is assigned to it. O, that's a terminal history. I don't assign anything to it. EF, that's a terminal history. I don't assign anything to it. EA, that's a terminal history. I don't assign anything to that. Okay. So here, non-terminal history, player 1 is assigned. Non-terminal history, player 2 is assigned. Non-terminal history, player 2 is assigned. Non-terminal history, player 3 is assigned, and so on. Okay? So again, we took care of this function by labeling the nodes, the non-terminal nodes. Okay? So the mathematical structure is a bit complicated, but the picture is actually pretty simple. Okay? So far, so good? So far, so good? Okay. Now, let's skip this. We said chance moves. So when chance moves, actions are taken randomly. So we need a probability measure that takes care of that random business. We'll get to that later when we do an example which involves randomness. So I'm going to skip this for now. For now, at least for the several games that we will be studying next, there will be no chance move. So when there's a chance move, we'll get back to that. Okay? So the information part. Okay? So for each player I, we have calligraphic I, script I, which is a partition of all the histories at which player I takes an action. P of H equal to I means that history H, player I takes an action. So we're looking at all histories under which player I takes an action. Okay? Again, let me remind you what a partition was. Okay? So a partition is of a non-empty set X is a collection of non-empty sets A1, A2, let me write it over here, non-empty sets A1, A2, AK, such that for any ij from 1 to k, if I is different than j, ai intersection aj is empty. So they are mutually exclusive. And the union of the sets gives you the set X is a non-empty, I should say, subsets of X. Okay? So they should be mutually exclusive and they should cover everything. Okay? So, okay. Okay. So what we need is, this is about the information. It's about what players know. Okay. I need more room. So let me erase this. I'm assuming you're done. So for player one, okay, for player one, the nodes that in which he takes an action, let me erase this and write again. So the empty sequence, the sequence consisting of EO, EF, EA. Actually, I might have some room. So player one takes an action at this node, okay, and player two takes an action at this history node. So in this case, it's very easy. E1, well, the nodes that agent one takes an action is only the empty history. So it's a set with only one element. There's only one way to partition it. That's it. For player two, again, there's only one history. Okay, so there's only one way to partition it. That's it. Okay, so for player two, it's more, well, let's write it. So I'll erase this. We'll deduce this from the picture. Script I1, the information partition of agent 1. There's only one history at which agent 1 takes an action. That's the empty history. So there's only one way to partition it. That's it. Script E2. Script E2 takes an action at histories. So let me write it here first and then AB, and then we'll talk about it, okay? So he takes an action at this state. State history will mean the same thing, or at this state, at this history, okay? So there are two histories at which he takes an action, okay? So I'm going to partition that. So one partition could be both of them in a single set, or another partition could be each of them on a separate set. The partition tells us what the agent knows, okay? So if two histories are in the same partition, we will deduce that the agent does not know which history has occurred, which state he is in, okay? If two histories are in different partitions, different sets of the partition, okay, then the agent can tell the difference, can tell whether he's at the first history or the second history, okay? So here, player two can tell whether he's in this state, whether does know if player one voted for A or voted for B, okay? So because of that, the structure we have is yes, okay? So because this history and this history are in two separate information sets, I conclude that agent 2 knows when it's his turn to take an action, knows whether he or she is at this state induced by the history A, or the state induced by history B. Okay? So for player 3, now there's more about that. We'll talk about this. For player 3, the histories that is going to take actions are A, B, B, A, B. Those are the 4 histories, 4 states that agent 3 has to take an action. So we said he does observe the action of player 1, but does not observe the action of player 2. So hence, because of that, we put these 2 histories in the same information set, and these 2 in the same information set. Okay? Because these 2 are in the same information set, okay, we conclude that when player 3 has to take an action, if one of these has happened, and it's player 3's turn to take an action, he or she does not know which one. Okay? The same thing here, but if this or this happens, player 3 can tell the difference. Okay? Because those 2 histories are in different information sets. Okay? So far so good? So far so good? Now there are certain things that we have to be careful about these histories that belong to the same information set. Let's say that the game was not like this, but was like this. Is that possible? So if player 3 is at this state, he has to choose between A and B. If player 3 is at this stage, he has to choose between A, B, or C. And he doesn't know at which state he is. Is that reasonable? Why not? Why isn't it reasonable? Well, I'll change the elements here. But you see, take your player 3. You do not observe the action of player 2. But just looking at the options that is available to you, you can deduce the action of player 2. So your player 2, you took an action, I didn't see it. But then somebody came to me and said, these are the only 2 actions available to you. Then I would immediately conclude that you took the action A. If they said these are the actions, you have to choose between A, B, and C, I would immediately deduce that you took the action B. Just by looking at what is available to me, I could easily deduce what you did, even though I don't observe what you did. So if that's the case, these 2 nodes cannot be in the same information set. Okay? So at any history which is in the same information set, the number of actions available should be the same. Not only the number should be the same, but assume that the available actions were different. Okay? Again, just by looking at what is available to me, I would immediately deduce what player 2 did. Okay? So if 2 histories are in the same information set, the set of available actions should be the same. That's what this says. Okay? So if you draw a game tree, we call this a game tree, which looks like this, you should say, oops, I made a mistake. That can't be true. Either this is not a C, or these 2 are not in the same information set. Okay? So far, so good? So, okay? So the set of actions available to agents at histories which are in the same information set should be the same. That's what that condition says in the language of mathematics. Okay? Any questions so far? Okay. And then terminal histories denotes the outcomes of the game. So we have a preference relation over the set of terminal histories. Okay? That preference relation we usually represent by numerical representation. So what we did was assign numbers here, which represented the preferences of the individuals over outcomes of the game or over terminal histories. Okay? So far, so good. So here, because there was 3 players, we assigned 3 agents. So here, for example, A, the outcome is A. A is elected. Okay? And then we write here numbers which represent the preference of player 1, player 2, and player 3. Any questions? Any questions? Okay. That's it. So, saying that, if I say, model this game in extensive form, what I want is this animal. But again, for our purposes, rather than writing this animal in a mathematical way, a picture that represents all these elements would suffice. Okay? So everything in here we can represent here. Okay? The histories are represented by nodes. Okay? The fact that there is a unique empty history means that every game starts with a single point. So you cannot have a case where player 1 and player 2 start the game. That's not possible. You can't have a game like that. Okay? So, so we talked about the histories nodes. The function, the player function, the function that assigns players to histories are represented by labels assigned to each non-terminal node. Okay? So 1 is assigned to the empty history, 2 is assigned to the history B, 3 is assigned to the history BB, and so on. So we take care of this by the function. For now, we didn't worry about the chance move. We'll get back to that. The information partition is represented by dotted lines. So if there is no dotted line, so if the picture is like this, it means that player 3 knows both the action of player 1 and the action of player 2. And then in that case, the partition would be like that. Each partition would contain a single history. Okay? So we can take care of this, again, on the picture by these dotted lines, dotted curves. Okay? And the preferences are taken care by assigning numbers to each non-terminal history. Okay? So that complicated mathematical object can be represented by this simple picture. Okay? Any questions? Any questions? Okay. So when I say model this situation as an extensive form game, what I mean is draw a picture like this. Okay? Which tells me who's involved, when they take an action, what actions are available to them, what do they know when it's their turn to take an action, okay? And what are their preferences over the outcomes, the results of this game. So far, so good? Any questions? Any questions? So then we can do some examples. Let's start with something very simple. The prisoner's dilemma game, okay? I claim that we can also represent it as an extensive form game, okay? So the district attorney first goes to suspect 1 and asks, do you confess or don't? So the game starts by player 1, suspect 1, taking an action. He has 2 actions available. So his actions will induce 2 histories. We label them with confess, don't confess. And then goes to suspect 2. Okay. And then, so it's suspect 2's turn to take an action. So that's how we label that. Okay. And then asks, do you confess or don't. So player 2, suspect 2 has 2 actions available to him. Confess, don't, confess, don't. And since player 2 does not know the action of player 1, we connect those 2 histories, those 2 states, with the dotted line, which represents that player 2 does not know the action of player 1. Okay? And then we assign numbers to the terminal nodes, which represents the numbers that we had in the prisoner's dilemma game. Okay? Now, one thing we have to be careful about is, okay, so this actually represents also the simultaneous move game. But so does this. Okay? So which one should I choose? Well, because they both represent the same game, okay? In both cases, player 1 does not know the action of player 2. Player 2 does not know the action of player 1. Okay? They're in a way equivalent. So the solution concepts that we develop should give the same result whether we model the game like this or like this, which will be the case. So that will be something that we will not have to worry about. Okay? Whether you model the game like this or like this, it will make no difference. Okay? Okay? So whenever you have, like in the voting game, I said we ask first player 2 and then player 3. It wouldn't matter if we asked first player 3 and then player 2. Okay? So, should we do one more example, a simple one? Well, the duopoly. We studied Cournot duopoly. We studied Bernard duopoly. Well, there's another kind of duopoly where the firms do not take actions as if they are taking an action simultaneously. Sometimes in some markets, for example, the small firms can make decisions faster, and they make a decision, and large firms, when they're taking an action, they see the decisions of the small firms. Okay? Because of the structure of small firms, sometimes they can act faster than large firms. Okay? And hence, when large firm decides on how much to produce, they already know what the other firm in the market is producing. Okay? So what we're going to do is we're going to study a market structure where announces how much it will produce, and then the second firm observes this and announces how much it will produce. And then just like in Cournot duopoly, they sell at the market clearing price. Okay? So how do we model this situation? Well, again, you always start with a single node. Okay? So the game starts. Who takes an action? The small firm. Let's say firm 1. Okay? So what action can the firm take? What are the actions available to firm 1? Sorry? How much to produce. Okay, so firm 1 will decide on how much to produce. Okay, which is what kind of an animal? It's a number. What is the range of those numbers? Sorry? From 0 to infinity. So if it's discrete quantities, I could go produce nothing, produce 1 unit, produce 2 units, produce 3 units, and then all the way to infinity. Let's, for the sake of simplicity, let's assume that there is an upper bound on what they can produce. Okay? let's call that alpha. Okay? So if firm 1 decides on how much to produce in discrete quantities, that's what will happen. But to be in accord with what we did when we're studying strategic form games, let's assume that firm 1 can take actually any non-negative, can produce any non-negative quantity. Okay? So then that will be complicated because not only I will have to draw infinitely many lines, it will have to be uncountably infinite. Okay? So the way I'm going to deal with that is, so I'm going to write the lower bound. I'm going to write the upper bound, let's call that alpha. And then I'm going to choose a special point, call it Q1. And to denote the fact that anything from 0 to alpha is possible, I'm going to draw a solid arc. Okay? So whenever you see a picture like this, you should understand that anything from 0 to alpha is possible. Okay? So far, so good? Okay. So after firm 1's decision, firm 2 takes an action. Okay. So again, I'll take this generic node, okay, and then write down what firm 2 can do. Again, I'll assume that firm 2 can produce any quantity from 0 to alpha. Okay. And let's say that again, take a generic node denoted with Q2. So this is the history that is denoted with Q1. This is the history which is denoted with Q1, Q2. And that's a terminal node. The game ends. We assume that firms prefer a high profit to low profit. So what I'll write here is pi 1 of Q1, Q2, pi 2 of Q1, Q2, where pi I of Q1, Q2 is equal to the market clearing price when the quantity in the market is Q1 plus Q2 times the quantity the firm produces. So that's the revenue of firm I minus the cost to firm I of producing QI units, just like in the Cournot duopoly. Okay? That's it. Okay? Any questions? By the way, we call this the Stackelberg. Well, it's a quantity setting Stackelberg duopoly. We could call it a price setting Stackelberg duopoly. Okay. Stackelberg is the economist who introduced this concept. So we have Cournot, Bertrand, and Stackelberg, and two versions of Stackelberg. Price setting, quantity setting. Okay? Any questions? Any questions? Okay. So we will work on more complicated models. By the way, these nodes are not dotted. So player 2, so if, I could have had something like that, which would actually correspond to, if I had dots here, it will correspond to Cournot's duopoly, exactly. Firm 1 does not know the action of firm 2. Firm 2 does not know the action of firm 1. So that would be turned into Cournot's duopoly. But that's not the case. We assume that firm 2 observes the action of firm 1 before it takes an action, before firm 2 takes an action. Okay? Any questions? Okay. So let's take a break. After the break, let's see how we analyze, make predictions or prescriptions for extensive form games.